Hello physics students. So I'm very excited for this video because you're going to learn about how people discovered something that was enormously important for the human race, and that's how to generate electricity. And if you think about that, think about all the things that we do with electricity. Of course, we have our lights, we have heat, we have appliances doing things like washing our clothes. We have entertainment like TVs and cell phones and Blu-ray players or streaming. And then there's in medicine, think about all the medicine that came about with electronics, MRI machines, all these different kinds of surgeries. So enormously important for humans, the figuring out how to generate electricity essentially ushered in the modern era and modern life and a lot of advancement. So it's going to be interesting in terms of the science, the physics. Also, I'm excited for the video because there's a lot of really cool demonstrations that I'm going to show you, so I'm excited for that. But a little warning, a lot of this is beyond the Regents curriculum, not necessarily in difficulty, it's just that on the Regents, they ask so little about magnetism. It's like almost like trivia of magnetism. Very disappointing. So I'm going to give you more information than you need for the Regents. And then at the end of the video, I'm going to tell you what to focus in on your studies to be ready for the Regents. So the first thing, in order to understand how humans figured out how to generate electricity, you've got to understand something called flux. So let's begin there. Magnetism 2, generating electricity. Flux is a measure of how much magnetic field penetrates an area. So like if I take a bar magnet and let's see, a little piece of paper like this. If I go like this, there's a north pole here, the magnetic field's going through the paper, that's flux. So we can express that mathematically. First of all, I put the word flux here because this is a Greek letter phi and it might be a little intimidating, a little confusing. I could have just written out the word flux. If this confuses you, this symbol, or it intimidates you, just replace it with the word flux. That's okay. But here's what it is. It's the magnetic field. B is the symbol we use in physics for magnetic field. B perpendicular. In other words, it's the magnetic field that's perpendicular to an area times the area. So when, for example, I have a piece of paper like this and I have magnetic field perpendicular to that paper, it's like poking through the paper, then I have flux. Whereas if I turn the paper like this and then I have magnetic field arrows going like this, then they don't go through the paper, so I don't have flux. So it's just a quantity of how much field goes through a particular surface. So here are some examples. Now, it's a little tricky because with magnetism, we really start getting into drawing arrows in 3 dimensions. So here's a rectangle, maybe like a piece of paper, and then I want to draw magnetic field lines coming out. So what am I going to do? Trace my pencil through the air like this? No. So what we do in physics to draw an arrow coming out of the paper is we draw a circle with a dot in the middle. This represents like an arrow aimed right at your eye. What you would see is the shaft of the arrow and then the tip of the arrow, the sharp point. So that's basically just kind of like, intuitive, and it also makes sense, but that's how we draw magnetic field coming out of the board like this. And here I wrote yes because we have magnetic field poking through this surface. This is an example where we don't have flux. We have magnetic field running along the surface of this chalkboard, and then I tilt the paper so it's like this, and you see the magnetic field never pokes through the paper, it just kind of runs either in front of the paper or behind the paper. No flux. If I were to turn the paper like this, okay, now it goes through, we have flux. But in this particular case, we don't. So I'll create a pause to give you a moment to copy these notes down. Now, the question is flux what creates electricity? All right? Does flux, magnetic flux, create electricity? What I'm going to do is I'm going to reconfigure the camera on some equipment so we can see, we can find out with a little experiment. So let me reconfigure. So we want to know, does magnetic flux, which is the magnetic field going through a wire loop times its area, does that generate voltage and therefore electricity. To generate the flux, what I have is a source of magnetic field, this horseshoe magnet, which is very, very strong magnet. Watch this. You hear that violent crash down. If I had my finger here, maybe it would even cut my finger with that violent attraction. So this is a very strong magnet which produces a lot of magnetic field. So that's going to help me. I'm going to get a lot of flux. You see how difficult that is to pull apart. Also, here's another little indicator. This is fun. You throw the paper clip in there and it gets trapped in the magnetic field. So then I have this wire coil here. The reason why the wire spirals around multiple times is to magnify the effect that I'm going to be trying to creating electricity. I'm going to use a little tape to hold it in the magnetic field. Maybe something like that. Another one on the back side. So I definitely have magnetic flux. This horseshoe magnet, this is the north pole, this is south pole, so the magnetic field lines are going from north to south, and therefore they are going through this wire loop. We've got a tremendous amount of flux over here. Now I want to see, is there voltage or current that's generated in these two wires, in other words, a voltage. To measure the voltage, what I have here is this thing called a galvanometer. Because this effect is not very efficient, because I'm using basically just like homemade materials, I'm not going to be generating all that much voltage when I eventually do. So this galvanometer, what it is a very sensitive voltmeter. I'm going to connect it to this just simple 1.5 volt AA battery. Not really a huge voltage. No one would think of this as a huge voltage. And watch the galvanometer when I just touch this to the positive here. You see the needle flies off the scale, right? So this 1.5 volts blows the galvanometer away because this measures very tiny, sensitive voltages. So if there is any voltage, this will be able to detect it. So let me connect first this wire here and now the other wire. So we've got a lot of flux. Let's see, do we get voltage? Nothing. No movement, no voltage in that coil, even though we've got a tremendous amount of flux. So what is it that creates the voltage and therefore electricity? What I'm going to do is just get this tape out of the way and watch what happens when I start moving this upward. Oh, it's tangled up. I'll start moving it upward. And you see the needle deflect while it's moving. As soon as I stop, the needle goes back to zero. So only while there's motion is there a deflection. Same thing going in. Moving, I got voltage, I stop, it goes away. Move it some more, I got voltage, I stop, it goes away. Move it. Only while I'm moving it do I get a deflection. Okay? As soon as I stop, the voltage goes to zero. So what that means is that we don't need flux. Zero flux also does not create magnetism. So flux doesn't, no flux doesn't either. What creates voltage is a changing flux. As it's changing, I increased it on the way in or I decrease it on the way out. Increase, decrease, and I get a deflection. So the other thing that's in this principle is the time. Look what happens when I move this out slowly. You see a very small deflection. It went just a little bit this way. And then if I move it in slowly, it moves very little the other way. Now what happens when I pull it out fast? When I put it in fast? In other words, the faster I make the change, the more voltage I have. This can be expressed in equation like this, which I'll write on the board in just a minute. But the voltage produced is the more you change the flux, the more voltage you get. And the smaller the time you change it over. In other words, the faster you do it, the more voltage you get also. This is the basic principle called Faraday's Law. But before I go on to the notes, I want to just point out that we don't just have to change, it's not only changing the magnetic field that changes the flux. We could also change the area right here. Because if I make area smaller, I get less flux. So let me show you that. I take this coil, and right now there's a certain amount of flux. Watch what happens when I go like this. What happened was I made the area go away. I didn't make the magnetic field go away, because it's still in the magnetic field. But the area changed. And I got a change in flux, and therefore a voltage. And then when I bring the area back, I change the flux again. Another thing I could do is I could change the direction. So right now, let me reshape this coil a little bit. Like this. I have flux, and it's steady, so I have no voltage. But rather than pull this up or crush it, I'm going to just turn it. Watch what happens when I turn it 90 degrees. I get a deflection. I turn it the other way 90 degrees. Here I have flux. Magnetic field's going through the hole. When I turn it like this, I go to zero flux because the magnetic field is not going through the hole anymore. It's just running along the top and bottom. So no flux. So then I change from zero to flux. I get a voltage. From flux to zero, I get a voltage while that change is happening. But here's another thing I could do. I could put a shaft here, an axle. And I could put a handle on here and I could start turning this. And watch what happens to the needle as I keep turning this again and again. The electricity oscillates back and forth as I turn it, one direction, then the other. And this is what we call alternating current, which is what we have in our outlets. And so that's how humans generate electricity. They get a coil in a magnetic field to turn, and then the electricity oscillates. If you turn this at the right speed, you'll generate the oscillation at the right speed that all our appliances run at. So there is the basic way, a tremendous advancement in technology. But here's a couple problems. Look, notice the wire is tangling up. If I keep turning this, eventually the wire will become so tangled it's going to snap. So humans had to figure out a way around that. What they did is they put like a electrical contact that's like a cylinder that spins on the axle, and there's two of them. And then over here there's what we call brushes, two contacts that touch these two rings, and as this spins, the wires don't twist because the contact is just a little bit of friction, but it maintains electrical contact and transfers the electricity outside of the spinning coil. So that's one thing. The other thing is, well, what do you get to turn this? Obviously, people aren't going to be doing this for us to get electricity and watch TV. So what you do is you use some kind of mechanical way. Well, maybe you have a shaft going here to a turbine. You boil some water by burning coal or something, and then the steam comes out and turns the fan blades, and then we get the steam turning the fan blades from the burning coal, and that generates electricity. But any kind of energy source that can create rotation will work. Like, for example, you could put the shaft here in a paddle wheel, and then the water falling down in the paddle wheel, and it'll turn the shaft. That's like in a hydro dam, when you have a dam generating electricity. You could use maybe wind, a fan turbine, and when the wind blows, it causes it. So anything that can cause a mechanical turning of a coil in a magnetic field will be effective as a generator. So I could show you an example of that here. You saw this earlier in the year, a hand crank generator, and there's coils in here that I turn, and I generate the electricity by the magnetic effects of induction Faraday law. So let me go back to the board now and summarize what we learned. So changing a magnetic flux through a wire loop creates voltage, generates electricity. So that's the first of the two techniques for generating electricity that we're going to learn today. It's called Faraday's Law after the physicist who discovered this thing about the universe. And here it is expressed as an equation. The voltage created in a circuit is equal to the change in flux over time. Again, if this intimidates you, write out the whole word change in flux. We're just concentrating on concepts today anyway, so if this is going to make more sense to you, do that so that it makes more sense. So the more you change the flux, the more voltage you get out of a circuit. But the smaller the time that the change occurs in other words, the faster you make the change happen, the smaller this gets, the more volts you get. So that's the concept, Faraday's law. Let's take a look at a couple examples drawn out. So what I have here is a wire loop and a light bulb, and this time I've got the magnetic field and I've got circles and X's instead of circles and dots. This represents the tail end of an arrow when it's flying away from you. Well, maybe I got to get closer for the focus. So you see when you have an arrow flying away from your eye, you see the feathers on the back of the arrow instead of the tip when it flies at your eye. So before we said that we would have a circle with a dot for the shaft of the arrow and the point of the arrow right there, right? So you could see kind of the sense of that vector notation. And then here we have the shaft of the arrow with the feathers. So this is how you draw a magnetic field, or any vector, by the way. It could be velocity, whatever. It's flying away from your eye, or in other words, going into the paper or into the board. So in the first example, the magnetic field stays constant. There's no change in flux then. We have the same magnetic field, the same area for all time, and so no change in flux, no voltage, so there's no light in the bulb. In the second example, we have the same circuit, but this time the magnetic field, it can increase or decrease. Increasing it will make the current flow in one direction, decreasing it will make it flow in the other direction. More information than we need for our purposes today. The point is any change, and then that changes the flux, which then makes a voltage, which could possibly, which will then make a current, which could, if it's big enough, will make the light turn on. One more example. Let me make some room. So this is going to be a little tricky, again, because I have to try and draw this in 3 dimensions. So let's see how we do. So let's see, let's go. Now, what I'm going to do is I'm going to take this wire and turn it so it's coming straight up and down like this, so it will look like this. In other words, it's perpendicular to this chalkboard. And so this is the final state. So here we have flux initial does not equal 0, but here flux final equals 0. So once again, we had a change. That means that during the change, there was voltage, there was current, and possibly if there was a light bulb in this circuit, it would light up. While you're turning the coil, as it's turning, you're changing the flux. Once you get it to this point and then you stop, and then the flux stays 0, then you have no current. If we started here and then turned it like this, then we would have the current, the light, the voltage again, because while we went from 0 flux to some flux, during that change, that's also a change, also a voltage, also a current. Okay, so let me create a pause to give you a chance to copy these notes down. Okay, so increasing, decreasing field, or turning the coil as we saw in the demonstrations. Now what we're going to do is look at the second method for determining, for creating a voltage. You could change the flux, as we just learned, but there's another way to create voltage. Let me reconfigure the camera, and I'm going to show you how to do that. So this second method doesn't involve changing the magnetic flux in a coil. what you use instead is a single wire. So obviously you can't get flux through the coil because there's no area. When we loop around, we get an area like that. So you just take a single wire, and I'm going to hook the galvanometer to both ends of the wire. Well, first I'm going to put it in the magnetic field. So here I go. I've got the wire in the magnetic field. Now this one's going to create much more subtle effect, so you're going to have to watch carefully, watch for the needle to move. So what you have to do, now again, there's magnetic field lines that go from the North Pole to the South Pole. So imagine all these invisible lines that go like this in between the horseshoe magnet. In order to generate this voltage, what you have to do is you have to slice through those magnetic field lines. And that means move this wire either down toward the floor or up toward the ceiling. So watch that. You see that little tiny deflection? Or I move it up, I get a tiny deflection. Down, I get a tiny. So I go like this and I slice the magnetic field lines that are going like this, these imaginary lines. If I move this way, I don't really get an appreciable deflection because the field lines are like this, and so what I'm doing is sliding this wire like this. I'm not slicing through them. I'd have to move them down. Like imagine these were spaghetti noodles and this was a knife. To cut the spaghetti noodles, you wouldn't go like this. You would push the knife down and cut through. So this doesn't do it. Also, this doesn't really do it because again, I'm just going like this, oh, you can't see, like this, and the field lines are not getting cut by this wire. Only down, up like this generates that tiny bit of voltage. So let's go back to the board and I'll summarize. So we had method 1, Faraday's law, changing the flux in a wire coil creates a voltage, therefore generates electricity. And now method 2, like we just saw in the demonstrations, that if you have a single wire, slice magnetic field vectors, then you will generate voltage and therefore electricity. So now what I'm going to do is try and sketch these examples on the board as best as I can so you could see the principle when you go back looking in your notes. So what I have here, example 1, I've got magnetic field lines that are coming out of the board, right, as I talked about the dot in the circle. So there are B lines coming this way, and then I take a wire and I go like this. Well, maybe I could take this here and I move it this way or that way. That's what I have here indicated by velocity in either direction. I put yes, yes. This does generate voltage and therefore generate electricity because if you imagine these magnetic field lines, when I move the wire, I slice them like this, or the ones over here, I slice through them with the wire moving it this way. Example 2. So I have, again, a similar situation. I've got magnetic field lines coming out of the board like this, and I've got the wire like this. Now I can move this, or I move it either down toward the floor or up toward the ceiling like this or like this. Notice when I move the wire like this, I am not slicing through the magnetic field lines. Again, I have to go like that to slice through these, or this way to slice through those. So moving it this way does no slicing, no voltage, no current, no electricity. All right, what I'm going to do is show you a couple more examples so you could really hopefully get this principle down. Okay, so another example would be, let's suppose we have this time magnetic field lines that run this way. So this is B, magnetic field lines. I've got my wire like this. I'll try and draw it nice and thick. And then I'm going to indicate velocity, some motions. Suppose I move like this, or like this, or I move it like this, or I move it like this. So let me demonstrate with this arrow. So magnetic field line, so I take the wire and I move it towards the ceiling or towards the floor or towards the right or to the left. In all 4 of those cases, I'm not going to be generating voltage because I'm not slicing through the magnetic field lines. I'm running along them, not slicing through. So I will indicate no, 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 and no for all 4 of those velocities. So same situation, but this time what I do is I take the wire and I push it down into the board, or I lift it out. And of course there's magnetic field lines everywhere. You know, there's above the board, behind the board, they're all coming this way through space, so I can push it in or pull it out. So we have to write that in words. And in this case, what do you think? Is voltage created? Am I slicing the magnetic field lines? The answer is yes, in both cases. Again, imagine I go in, I'm slicing through those field lines that are running this way, or if I pull out like this, I'm going to be slicing through magnetic field lines that are running above the board. So both those create voltage. So let me create a pause to give you a moment to copy these notes down. Okay, so we're not done with demonstrations. I have more exciting demonstrations, really cool, interesting ones. What I'm going to do is next move on to talk about how alternating current, the current we have in the wall, as I mentioned, it oscillates back and forth, is really conducive to capitalizing off these changing magnetic flux, inducing a voltage and inducing a current. You can transfer current and voltage from one coil to another that aren't even touching. So let me reconfigure the camera to show you those actions taking place. Now, to see the next set of effects, I have to introduce another concept. Now, you already know that a bar magnet produces magnetic field, and one of the ways you could detect that magnetic field is you could see that it attracts iron, like in these paper clips. Another way is that you could see it interact with other magnets. Like if I bring this other bar magnet here, you see that the opposite poles, the north and the south, attract each other. Whereas if I put like poles next to each other, south and south, they repel. Or north and north, they also repel. So that's a way to detect the magnetic properties. So the new concept is that another source of magnetic field is current. What I have here is what we call a solenoid, or you could even call it an electromagnet. What it is just a spiral of wire around a cylinder. And when I pass current through here, it's going to generate a magnetic field, and it will essentially turn it into a bar magnet. So let's take a look at that. So I turn this power supply on, and you see that it repelled this away, so that must mean that this electromagnet or solenoid, what it is right here is if this is a north pole, then this is a north pole here. So it repels the north pole of the permanent magnet, and you should see it attracting the south pole, which it does. When I let this go, it attracts to here. So this is essentially the same as this in its magnetic effects. We could also see evidence of its magnetic properties by putting an iron bar through here to magnify the effects, and you see here no magnetic effect or very little. I'm not picking up any paper clips. I turn the current on, and suddenly I pick up paper clips, I shut it off, and I shut the magnet off. So this is, again, a magnet that can be turned on and off with electricity. It's going to demonstrate our principle of generating electricity. What I'm going to do is turn it on, and so I have a magnetic field that is produced by this, and it's going to be inside this, which is yet another wire coil that spirals around from one side to the other. So when I turn this on, what I have is flux in the outer coil, because I have a magnetic field inside this outer coil, and so there's flux there. So see this also, you could see that evidence. I'm going to hook it to the galvanometer, and we're going to see if we can get electricity in the second coil. And you see no deflection, and you should be saying, of course, I know exactly why there was no deflection, because you don't need flux, you need a changing flux. This magnetic field inside this outer coil is right now steady, constant. No change in flux, no voltage in the outer coil. We don't see the needle move. What I need to do is change the magnetic field. I could do that by turning the magnetic field off by going like this, and you see there's a deflection when I turn it back on. So right now, again, steady flux because there's no flux, but then while I'm turning it on and changing it, I get a voltage induced. Right now, we've got a constant magnetic field, no voltage, only while I'm flipping this dial around and changing it. And you could see when I'm turning this current on and off, I got the needle to oscillate again, just like I did when I spun that coil in the horseshoe magnet. So I can transfer electricity from one coil to another. Look at these, they're not electrically connected at all. This is all insulation here, and I'm putting it in, and I'm not connecting the coils, but somehow I'm transferring electricity from one coil to the other because of the magnetic effects. So magnetism transfers electricity from one coil to another without an electrical contact. And again, I can get alternating current by getting the current to alternate in this inner coil, and then it'll alternate in this outer coil. And so that's an important principle, because now I'm going to show how alternating current in one source makes alternating current in the other coil through the magnetic transfer with another setup. So let me reconfigure, give me a moment. So now I have even a bigger coil here, and you see that right now it's, like I said, it's like an electromagnet and there's no electricity, so it's not attracting this piece of iron. But if I hook this power supply up to this cord, and I turn this on. Oh, let's see, do I have it plugged in? Yes, okay, and I turn this on. Then I have a current in this coil, and you see now the magnet is attracted. I could even pick up this whole heavy coil through that magnetic attraction. Now what I'm going to do is I'm going to take this light bulb, which is connected to a coil of wire, only spiraling around, not connected to any battery source, and I'm going to put it on here, and we're going to see no light. And you should know why. Why didn't that light come on? We have magnetic flux going through the coil. Why no voltage? Why no electricity? Well, hopefully you said, I know why, because we had flux, but it wasn't changing. So no changing flux, no voltage, no current, light doesn't come on. So the problem with this is what we call DC power. It's a direct current that's steady in the coil. The flux is not changing. So I'm going to replace it with something of current that actually oscillates. And to do that, you may have noticed that this has a plug that can go into a wall outlet. This is going to be plugged straight in, and I got to say, if you have a coil like this at home, which I'm sure you don't, but if you did, do not try this at home, because once I plug this in, the electricity will be delivered to these two posts unprotected. If I touch these, I'll get electrocuted from the wall outlet without any fusing or protection. So dangerous, this coil. But when I plug it in, the wall outlet creates oscillating electricity. So the current in this coil will oscillate back and forth 60 times in 1 second. And that will, instead of creating a steady magnetic field, it'll create a magnetic field that oscillates 60 times in 1 second, which will be the changing flux per time, which will create a voltage. We should see the light come on. So let's see. And there you see, oscillating magnetic field through this coil, and therefore it creates a voltage in this wire loop, which makes electricity oscillate in the coil and turn the light on. This brings me to another important application. What I did is, as I said before, I'm transferring electricity from this coil to this coil without any electrical contact, only through magnetic effects. Furthermore, this little light bulb, if I hooked it straight to the wall outlet, it would burn out. It's too many volts. What I did is I took voltage here that was 120 volts, and because of the magnetic effects, it changed the voltage to something around 3 or 4 volts to safely operate this bulb, which is another very important thing of oscillating or alternating current. Now, you may, let me remind you of something I showed you earlier in the year. I showed you those power lines that were I think 600,000 volts, and the people had to go work on those power lines by being dropped off in a helicopter. If they put a ladder up to those wires, the electrocution would vaporize them. That's how high the voltage was. To deliver electricity from one part of the country to another over many thousands of miles, you need extremely high voltage. But if you put that voltage into someone's house, it would catch the house on fire and kill people inside. So you have to find a way to change the voltage to a different value, which brings me to the next thing, what we call a transformer. So let me reconfigure the camera to show you what a transformer is and how it operates. So I'm sure you've seen transformers on the streets, on telephone poles. You may not even known that they were transformers. They're basically like these gray cylinders that look almost like a little garbage can or a decent-sized garbage can at the top of a telephone pole. They transfer voltage. They change the voltage from one voltage to another. This is also a transformer. Of course, it's one for a classroom, so it's not as efficient, but the nice thing is we could take it apart to really understand how it works. So what I have is actually two coils. This is what we call the primary coil, and I don't know if you could see it, but it says right on it that it has 800 turns, and you might be able to see inside a really fine wire that spirals around this like rectangular block 800 times going around. And it's around this iron so that the magnetic field that's going to oscillate in this alternating current will be going through this iron bar, and then we're going to connect it here so that the magnetic field gets piped up in a sense to this second coil, and this coil, I don't know if you could read it, yeah, 12 volts, and it only has 80 turns. So the wire, instead of going 800 times around, only goes 80 times around. And when I put it like this, what I'm doing is I'm linking these two coils magnetically, kind of like those two solenoids or two cylinders that I had earlier, but this is more efficient linking of the two coils. Now, as this coil gets electricity from the wall at 120 volts and it oscillates back and forth in this coil, it's going to create an oscillating magnetic field that gets piped around and oscillates up here. So that it gets sort of brought up to this one. But the difference in coils allows a different amount of magnetic flux changing, which will then create a different amount of voltage. I'm going to plug this in, and it's going to buzz a little bit because of the vibration, but basically what I can do is I can measure the voltage coming into this primary coil with this multimeter, and if I touch over here, you'll see that coming in is 120 volts. I mentioned this already, that the wall outlets in America operate at 120 volts, so that's all I'm measuring, the voltage out of the wall, which is what's going into this primary coil. Up here, though, the secondary coil, if I go like this, then I see I only get 12 volts, 12.9 instead of 120. Let's just say 12 and 120, just to make it easy. And you might notice 800 wire turns, 80 wire turns. There's a 10-to-1 ratio here in the number of coils. And we've got 120 volts and 12 volts, about a 10-to-1 ratio in the voltage. So that's essentially how a transformer works. By making fewer wire wraps up here, you get less voltage than the primary. I'm going to shut this off and I'll switch it out with another coil. This coil has, instead of 80, it has 200 turns. This has 800, so it still has less by a factor of 4, and it's labeled on it 30 volts. So let's see, if I put this in, you'll see that indeed we do get that voltage. Plug it in. So again, primary coil gets 120 volts with 800 turns. What does 200 turns get? Well, maybe I'll let you think about it for a moment. What do you suppose this voltage is? 800 turns, 200, 120 volts. This is, let's find out, 32. Well, about 30. Let's say 30 just to make it easy. So we had 120, 800 turns, and then we had 1/4 as many turns, and we get about 1/4 the voltage. 120 divided by 4 is about 30, what we got there. So that's what a transformer is. Before I go back to the board, I just want to mention that notice all these coils here, they're fewer than 800 turns. I've got 200 turns, I've got 40 turns, and then I got, well, the third one was 80 turns. All less than 800, and all of these give me less voltage. The beauty of alternating current is, what if I wanted more voltage than 120 volts that comes out of the wall? Instead of 800 turns, maybe I have 8,000 turns up here. And then it goes the other way. I get more voltage in the top coil than I get in the primary coil. So you can increase the voltage with the transformer or decrease it depending on the ratio of the wire wraps in each of the two coils. So I'm going to reconfigure, go back to the board so we can summarize what we learned about the transformer. So we saw a transformer. It's two magnetically linked coils, and here's a diagram of a transformer, a schematic, of course. You know, this is just very oversimplified. You have one coil with a certain voltage coming in and a certain number of wire turns. And on this side, we have a different number of wire turns and a different voltage. And so the voltage gets transmitted without any direct electrical contact. The coils are really electrically isolated. They're only magnetically linked. And again, this only works with alternating current, because then the magnetic field will oscillate. As this current is oscillating, it creates an oscillating magnetic field, and that changing flux then creates a voltage. A direct steady current will create a steady magnetic field, no changing flux over here, so no voltage will be transmitted. Now the voltage relationship is just, you could find it by a simple ratio. Voltage here over the number of wire turns equals the voltage here over the number of wire turns here. And you could make less voltage, as we saw in the demonstration, but you could also make more voltage, as I mentioned. So let's take a look. Oh, let me just create a pause to allow you to copy these notes down. One example. So we've got in coil 1, this is basically what we saw in the demonstrations. We got coil 1 with 120 volts coming in and 800 wire turns, and coil 2 only has 80. So what is the voltage in coil 2? We just use this very simple basic relationship. We put in the voltage in turns for coil 1, and then the voltage here is unknown, the wire turns, and we get 12 volts. So let me create a pause to allow you to copy these notes down. All right, so I just want to emphasize that we can get more voltage out of a transformer. It can make, we saw it made less voltage, but you could also make a transformer make more voltage than what it's starting with by simply making this number bigger than this one. So if we put 8,000 here and this is 800, when we multiply, we'd get, instead of 120, we'd get 1,200 volts, more volts coming out of the transformer, so they can make voltage go up or down depending on how many wire wraps you have. So that's it for the information today. I hope you had as much fun as I did, because remember, we saw, or you saw, how humans invented techniques to generate electricity, which ushered in all the great things that we do with electricity now. So one was Faraday's law, changing the flux in a coil. And then the second was slicing a wire through magnetic field vectors. Now, as I said at the start, this video has way more information than you need for the Regents test at the end of the year. So I just want to tell you what to focus your studies on for the Regents. The thing that the Regents most emphasizes, or I should say the only thing it emphasizes out of all of this, is the generating electricity by slicing magnetic field wires, the method, magnetic field lines, the thing I called method 2 for generating electricity. So what I would recommend is, at this point, at the end of the video, go back in your notes and make sure you really understand that method for generating the voltage, and if you don't fully grasp it, then ask me in class tomorrow. So that's it. I hope you enjoyed all the demonstrations, like I said, as much as I did, the physics knowledge of how to generate electricity, and I will see you in the next physics video.